Micah Acinapura is a software integration engineer from the American Museum of Natural History in New York City. He showcased OpenSpace, an open-source interactive data visualization software designed to visualize the entire known universe and portray our ongoing efforts to investigate the cosmos. OpenSpace brings the latest techniques from data visualization research to the general public. OpenSpace supports interactive presentations of dynamic data from observations, simulations, and space mission planning and operations. You can visit the Hayden Planeterium at the American Museum of Natural History in New York City for the in-depth presentation. OpenSpace is free to use, but it does require a fairly powerful computer with a dedicated graphics card. Check out his work, links in the description box below.
Hi, welcome to the Space Apps Showcase at Open Data Week, sponsored by the Pit Lab. So thank you for welcoming us here. My name is Nate Cooper, and I am the local lead for New York City for NASA's Space Apps Challenge. It was a hackathon that was held last year in October worldwide. So in New York City, we had a couple hundred participants building apps out of space in NYU campus. But there are 100,000 participants worldwide. And in this challenge, it's basically NASA way of kind of engaging the public with open data that they generate. NASA has a mandate to, for every project, make all of the available data public. And the Space Apps Challenge is kind of an open call for people to do really cool things with this data. So they generate a list of challenges. We run a 3-day event with kind of a culmination and a winning team, and there's several categories for winners, but they build things like games or educational materials or apps. I'm joined here today by two presenters, and in the second half of the presentation, you'll actually see some of the people who built things at Space Apps last October. So our first presenter is Micah, who works at the American Museum of Natural History. He was a judge. One of the cool things I want to call out was the winner of the category that you judged got to actually show their work on the planetarium, which was a really cool experience. So Micah, I'll let you take it over and show us some cool things about this project you're working on.
My name is Micah, as Nate said, and I work at the American Museum of Natural History at the Hayden Planeterium. And in particular, I work on the software you're looking at here, which is called OpenSpace. And OpenSpace is our open source data visualization platform. We're funded on a grant from NASA, and we partner with university in Sweden, Linköping University, and we make this open source data visualization platform. And sometimes people ask me, well, what does that mean, open source data visualization platform? And I say it's focused on NASA data and astronomical data. And then they say, well, and I say, well, it's like Google Earth, but for the whole universe. And so like that's what you're seeing here. But what I'm talk about is a bit about how everything is data driven, and everything that you're going to see is all data. And so starting out, we're just looking at a 3D model of New York City. And this is actually part of the NYC Open Data. And this comes from the New York City Open Data website. And it was put together from their website and incorporated into OpenSpace by one of our users. And now we're able to show it. And so often people don't think of a 3D model as a type of data, but it's definitely a type of data. It's coordinates in a mesh about where these 3D things are. And then in the background, we have the map of Earth. And that is data taken from satellites. And so let's take off of Earth and take a look at that view that comes from the satellites. We'll look at maybe some of them and talk about some of the data there. And so everything that you're seeing here, people don't always think of a picture as data, but a picture is an amazing type of data. It's a super wonderful type of data to look at, work with, and explore. And as we zoom out, we're going to see that the map of the Earth changes, and we're going to see a different data layer attached to Earth, and that's going to be from a different satellite, which is going to show us the clouds. And so here we have data, and now this data is actually yesterday's clouds, and so we're getting data from the VIRRS instrument. And so where is this data coming from but satellites that are orbiting the Earth, and they're capturing it, and they're like basically taking these pictures, beaming them back. Scientists and computer programs are stitching together those pictures. And then here we have a bit of a visualization of the satellites themselves. And so what I can do is actually I can speed up time a little bit, and we can watch these satellites move around. And so what we can see is like different types of satellites, and different types of satellites are used for different, some are used for communication, some are used for science, some are used for weather. And here I can even like highlight, like one thing I'll do is I'll highlight maybe these, the GPS satellites. So now these orange lines here are GPS satellites, and these are the data, you know, these satellites are used by your phone every day to give you that little blue dot. In this case, what I'm visualizing here is data that comes from a website called Celesttrack, and they get it from NORAD, I believe, and they're basically tracking elements in the sky, things that they see in the sky, and they track them, and then they provide this data that's called a two-line element file or a general perturbation file that gives you information about the orbit of items. And so you can see these ones that are closer into Earth are moving a lot faster. Here we have some of the brightest things in the sky and some recent launches. And then we had our GPS, and now you might notice this band that's a little farther out. These are the geostationary satellites, and the idea is that they move with Earth so that they could always take a picture of the same surface over and over again. And so being at a certain distance is a way to do that. And so here we're visualizing the data of their orbits, but it also helps you to like understand concepts and stuff. Before we leave the Earth here, now we've went ahead in time to today. And so here you can see one aspect of the data is the data is not always ready. So today hasn't happened for the whole Earth yet. So we only have part of the picture available. And so one of the things that I wanted to turn on, these satellites are, you know, not just collecting pictures of the Earth, but they're also collecting data about all sorts of different things. Here I've turned on a colorized map of sea surface temperature. And so we're seeing the temperature of the surface of the ocean. And this is like what we call a temporal data set. So I could even like go back a day and it will load the day before, and go back a day and wait for it and it'll load. And I can actually progress through, and if I get up close, I can see local changes that happen in the temperature on the surface of the ocean. But generally, when we're looking at sea surface temperature, we might change like months in advance to see changes like in seasons and see how the temperature kinds of move up and down across the equatorial band. So, you know, Earth is a very important a data point for NASA. It's our favorite planet. It's the one we live on. It's the only planet we know of that has life on it. And so we're capturing lots of data about it, and we're visualizing lots of data about it. But it's not the only cool thing to look at that we have data for. And now I've turned on some more lines in the sky, and we do a lot of orbit lines here and to show where things are moving. And this is what's called ephemeris data that comes from NASA, which is kind of a fancy way of saying where things are when. Here I'll brighten up the moon's trail so we can see it a little better. So now we're seeing the orbit of the moon around the Earth. And that is its own type of data, and we use that to know when there's going to be eclipses and stuff. But let's go visit the moon, take a look. Of course, the moon has really cool imagery data, looking at pictures of the moon. The moon is beautiful. We see it in the night sky, and maybe some of you have seen pictures of the moon from the Apollo mission. But here we all have all sorts of other orbiters from ESA, JAXA, and NASA, all orbiting the moon and taking different types of data. So like here was an interesting one of a map on the moon of where helium was likely to be found. And so basically this is data from the LRO and Kaguya combined. Different instruments on different satellites were combined to figure out where there might be, and this data is actually streaming from a server on NASA, from the NASA Trek server. And what they've done is they have the scientists analyzing where they think there will be helium, where they think there's even more likely to be helium, where they think it's less likely to be. And so this red one is the one that's like, here's the best places. Now, the thing is, this is not actually where we're going to be sending astronauts to the moon. When we go back, we're going to be sending them to the pole of the moon, and we're going to be sending them to what are called these permanently shadowed regions on the moon. And these are craters that basically they never see the sun. And so these craters they're called PSRs, permanently shadowed regions. So here the data that we're looking at is pictures from the Lunar Reconnaissance Orbiter. And it's from its wide angle camera. So that's just a satellite that orbits the moon, just like our satellites that orbit Earth. And here Shackleton Crater is where they think they're going to go with the Artemis missions and the future of humanity on the moon. And one of the cool things that we can do with our data here is we also have data from a laser altimeter. So the Lunar Orbiter Laser Altimeter, and that's altimeter means getting altitude data. So it's a laser, basically they have an orbiter going around and it's shooting a laser down. And so the data is like how fast the laser bounces back to the sensor, which is telling you like how high are the mountains and how deep are the valleys on the surface. And so that type of data gets combined and turned into a map. And so here we can turn on this data from the lunar orbiter laser altimeter, and we can see inside of this permanently shadowed region. So this area that never gets any light, we're actually able to see inside of it. Look what it looks like inside of the crater, see the central peaks and the regions inside of it. And this is where our astronauts are going to go and explore and hopefully mine for ice that they'll turn into fuel and water and oxygen. And so that's just one of the types of data that we like to augment our pictures with. So a lot of times this elevation data is really important on planets and stuff. So now we're going to zoom out and we're going to look at another type of data, which is similar to the satellites, which is data that comes from the NASA JPL Horizons, their small body database. And this is data about asteroids in the solar system. So here's Earth orbiting around the sun, and we'll kind of zoom out and we'll get what is hopefully a familiar look of the solar system with some trails. There's our inner planets. Let me attach us to the sun. You might see some other lines. I'll talk about those in a second. And now we're seeing the outer planets here. And so here we're going to turn on the main asteroid belt. And so this is data about all the asteroids in the main asteroid belt. And this is data that anyone's able to download from JPL Horizons, from NASA, get it, and find out all these characteristics about different types of asteroids. They've already segmented the data for us. Some of these, here we're just looking at main asteroid belt, but let me turn on Jupiter Trojan asteroids. This is an interesting data set. You might have seen some videos online about Jupiter is protecting Earth from asteroids. It's talking about these asteroids, the Jupiter Trojan ones that kind of move in conjunction with Jupiter. Sometimes people say, Jupiter is hurling asteroids at Earth, and it's the same asteroid. They're talking about the same thing. And one of the cool things about our simulation here is we can actually increase the rate of time and now a moving time at 7 days per second, and we can watch these asteroids move around the solar system. And so here, again, this is data visualization, right? So what we've visualized the orbits of the asteroids, and we've gotten data about the orbits of the asteroids, and we're showing them moving in conjunction. You might see this yellow line here and wondering, what is that? Maybe I will actually pause time and jump us back a couple months, 2, 3, oh, got to go a couple more months back. This is an interesting piece of data that we also got, I believe, from the JPL Horizons, which is for the 3I interstellar asteroid. So if you've heard of this, this was the third interstellar asteroid that had come and visit our solar system, or that we have detected visiting our solar system. And there was a lot of talk of it about, is it an alien spacecraft visiting our solar system? And one of the things about it was that it was in the plane of the solar system with our planets. And here we can use that orbital data to really show you that how it really was like kind of more in the line of plane of the planets. If we were to compare that with the trail of other interstellar visitors that we saw, such as the Oumuamua that I've just turned on in purple, or the Borisov one that was found afterwards that I'll turn on here in green, we can see those have much more of a parabolic trajectory than this yellow one that is the 3I Atlas kind of coming in just along what they call the ecliptic of our solar system. And so this is the plane of our solar system that all the planets are in, which again is part of that ephemeris data from NASA about where things are when. And so that's a big, important data point of space, of where things are and when. And so one of the, here we just saw some of these two interesting groups of asteroids, the Jupiter Trojans and the main asteroid belt. But I thought I would also show one that I'm really interested in, which is the trans-Neptunian asteroids. And this data set contains a lot of bodies from the Kuiper belt, what's known as the Kuiper belt, which is what includes Pluto, which is like a icy, rocky worlds that are out, like far out in space. And you can see compared to the main asteroid belt, these are really far. Main asteroid belt is kind of really close in. And so one of the interesting things about this is we think about what are the limits of our solar system. And if I turn these back off for a second, we see those trails of our solar system and then those interstellar visitors. Maybe I'll turn those off for a second. But this is one of those data sets that helps me to understand and push the boundaries of like what is our solar system, because here we visualize the trails, but you might have noticed with our solar system too, we don't visualize the full orbit. We kind of have, we decay the data off the end and don't show the end of it, but I can actually adjust that here and show more of their full orbits and show their full orbit trails. And we can see that some of these trans-Neptunian asteroids actually orbit way far out, super far away from basically from the sun. And some of these are really going like, here I've turned on a 1 light year grid. So this would be like 1 light year across halfway. And so we could see like some of those, like one of those asteroids, the orbit is going out to half of a light year away. And so here, I've just turned on a grid. Basically, the most basic, simple type of data visualization we could imagine here is just showing length in space. I've just visualized 1 light year, but it can be a powerful thing to do. And so it's like maybe not NASA open data, but every type of data is relevant and can be used. So now we'll zoom out. We're out in the stars. And here we have interesting types of data sets like about exoplanets. And so we tap into like the NASA exoplanet archive. And this is like data about exoplanets that have been found. So exoplanets are planets that are found around a star that is not the sun, so stars that are out in the Milky Way. And so we want to like visualize those systems and the data that we have about them. So I'll go and visit maybe the most famous one, which is called TRAPPIST-1. This is one that has many rocky worlds in what's called the habitable zone. So a big important part of data about a star is its temperature and its size and what those mean to where liquid water might be able to exist in an area around the star. And here we're visualizing the orbits that have been determined by astronomers capturing data. Basically, they look at the light of the star, and they watch as the data they capture for the light of the star changes and varies. And when they see it dipping and getting dimmer at a repeatable pattern, they're able to determine that those can be planets going in front of the star and blocking the light. And one of the interesting things that we visualize here about the data is the uncertainty of their orbits. So if we look here at one of them, maybe, no, that was C, I gotta find E, TRAPPIST-1e. This one, the planets in our solar system, we just visualized with a trail, but the planets outside we visualized with a disk, saying it might orbit anywhere within that disk, and that might not look like a big difference, but that could be tens of millions of miles or something. So the data here now gets into like levels of uncertainty. And what does it mean to have like uncertainty with the data? I always think that's interesting, when we're talking about the data, is the uncertainty, and, not just like what we know, but how we know what we know, and to be honest about which things we do and don't know and stuff. And that's always like uncertainty leaves room for more exploration in the data and more science to happen. So one of these cool things, now I've pulled away and we're in a 3D like map of the stars. There's our 1 light year grid from Earth over there. But as I pull away, so now we're in a 3D database of the stars. This is the Hipparcos database, which contains, this one I think has 186,000 stars in it or something like that. But basically the positions of these stars contain their own level of uncertainty. And so now I've turned on these star distance uncertainty bars. And what we can see is that some stars, we know their position very well, but some stars we don't. Like this star right here that seems to be very close to us, but has a distance uncertainty of 4 light years somehow. This one that's really close, we still don't even know where it is within 4 light years. So here we see different colors representing different ways of how we know the uncertainty and stuff. But even within a close portion of our Milky Way, the distance of the stars has like a huge level of uncertainty to it. So one of the really important aspects of data visualization and working with data is like knowing the uncertainty around your data and where it's going to work. And so now we're pulling out and we're seeing like basically these stars, these lines of uncertainty are kind of pointing inward towards the sun and towards where we are and our place like in the solar system. But I'll turn that off, and maybe I just turn on this blue ball that represents where we are in the solar system, in the galaxy. Now we're looking at data, and this is some of the first data. Actually, this is the first data that I'm showing that wasn't captured from something. So now we're looking at a simulation data that was a simulation done by the National Astronomical Observatory of Japan about our Milky Way. So we actually don't have any pictures of the Milky Way. If you think about it, like if you were like inside a really giant house and you could never go outside that house, you wouldn't be able to have a picture of the outside of that house. And you say, well, okay, can you fly a drone outside of the house? Well, in our case, it would take 200 million years flying at the speed of light to get our drone outside of this house. And so here we actually have to visualize like a simulation of the Milky Way. And so we have all this simulation data for that they created, and we use that. And then another one would be here. We're showing the sun's orbit around the Milky Way. And this is here we've simulated based upon what we know about the sun's motion and the strength of the gravitational potential of the Milky Way. And so here we don't have data of where the sun will go in the Milky Way, but we're able to visualize data that was created by scientists who were informing it. And so those were the two pieces of there that were not like observed data, whereas now when I pull out and reach, well, actually before I go out and see the galaxies, I'll turn on one more data set, which now we're back to observed data, which is these Milky Way streams. So this is from new satellites that are capturing data, in particular the Gaia satellite that was giving us data about stars in our Milky Way and their motions and where they're going. We found that there's these like streams of stars that are like traversing around our Milky Way that come from different dwarf galaxies that interact with our Milky Way and kind of like whip through them and pull these stars around and stretch out these clusters of stars into streams and stuff. And so this is data that was compiled by a scientist that came from other papers and stuff like that. And I was able to get the open data that he had just posted on his website and transform it and bring it in here and show it. But this is all like data that was coming from the Gaia satellite. And so now we're going to pull out and we're seeing that that's like our Milky Way and these like little streams and dwarf galaxies that we're like eating and kind of whipping around. And now as we zoom out, every dot, instead of being stars like they were in the previous one, now every dot becomes its own galaxy. And so every one has hundreds, potentially hundreds of billions of stars just like ours, potentially trillions of worlds in every single dot existing here. And this is our local universe, and we're part of what's called this Virgo supercluster. So here we've colorized the data to help you to see the distribution of the galaxies and the densities. And this is if you've heard of what's the cosmic web. This is what the cosmic web is. It's where the galaxies have grouped together through time and gravity to create these like lumps. And here, we just take the data of their positions and also the relative density of the region is what we visualized here with the color mapping. And now we pull out into a deeper survey, which is the Sloan Digital Sky Survey, showing us that structure even farther and deeper out into the universe. And one of the things about looking at data in the universe is the farther you look, the longer that light had taken to reach us. And so that data is actually from earlier times in the universe. And so as we zoom out and we look at the data from the earlier times in the universe, we see less of that structure because the universe didn't have as much time to kind of gather and create the gravity that, not create, but like gather together because of the clumping. And so as we zoom out, we see less and less of that structure because the data is letting us see further back in time. And we finally reach what's like the edge of our cosmic horizon, which is the cosmic microwave background. This is data from the Planck satellite, which is like measuring this, like what's the cosmic microwave background is data on the like minute temperature differences in like quote unquote blank space. They like look out into space where there's nothing and try to see what is the temperature difference there, because like this is what they call the residual heat from the Big Bang. So basically like the idea is they're when they were building some telescopes, I forget what year, they like could not get this noise out of their data. And they said, what is this noise in our data? And then they pointed everywhere and they found everywhere there's noise. And what is that? But that noise is actually signals of these temperature differences in the microwave radiation. And so now we're going to zoom back into this data through the universe back closer to our time, and we will come back to our solar system where things are a little more familiar and graspable, and maybe at scales and distances that we're more used to. Let's turn off our Milky Way streams here. Get rid of our sun orbit. As we come back, I'll I used this blue dot to show us where we were in in the galaxy. This dot is actually also another piece of data visualization. It's like it's visualizing like a time boundary in space that winds up to be distance. And so this is representing like maybe I think 85 years across, where this is representing like how far our radio signals have reached in space. Basically, 80 years ago is when the radio signal started to being strong enough to penetrate our atmosphere and emanate out into space. And so this sphere is kind of showing like where our signals may have reached by now. And so one of the cool things is we like to combine that with the data of the exoplanet systems about like where have we like found exoplanets. So now I've turned on these blue circles where we circled every star at which we found an exoplanet. And so if we like combine, like one of the things we love to do is combine the data to show context. So here we're combining the data of like where have our signals reached and where have we found planets to show that like basically all of these planets within this sphere could have potentially heard from us. And so that's kind of like a fun one to do. And so this is like a different type of visualization of that exoplanet database, whereas before we were visualizing the data of a particular system. Now we're visualizing like the catalog as a whole to show its distribution across the sky and show everything that we've seen. Now we're just coming back to Earth. We've got our grid on. Let's get rid of that. Thank you very much. Back to our solar system. There's our sun. We've got the orbits of our planets and our asteroids. And you know, if we take a stop off at Saturn, we can see that some familiar things happening. You know, in the Milky Way, we saw these streams of stuff orbiting around the Milky Way, but then we saw like the disk of the Milky Way, which is like the flat coalesced stars, but there's all this crazy stuff happening orbiting around it. Saturn, you may or may not have heard, has a lot of moons. It has like 70 or 80 moons. So here I'm visualizing the orbits of these, what they call the minor moons of Saturn. So it's this chaos of stuff like orbiting around it, but then it has its major moons, which have like coalesced into the flatness. So if I turn off the minor moons here, we see now the major moons are more coalesced into the disk. And then Saturn, of course, famous for its rings. And so if we think about like Saturn's system as like a microcosm of what we saw in the Milky Way, where there's the chaotic stuff orbiting around, but then there's the flattened thing. And then we could actually think of our own solar system as the other microcosm. So we can see that at 3 different scales. So here we have all the planets and the main asteroid belt that are in the flat plane of the solar system. But then when we looked at those trans-Neptunian asteroids, we saw well, maybe they have their long trails on still, but we saw that they had these more chaotic orbits and going around and stuff. And so we see these like here, hopefully the data visualization has helped us to like also learn some concepts and not just, not just like learn things about the data itself, but using the data to learn about concepts in general. And here in particular, we've just used it to visualize about gravity and the shape of things and the shape of gravity and how it affects matter. And then we'll take us back to Earth, maybe see if there's any questions.
So you were sort of controlling things live. Is that what's done in the planetarium as well, or are there sort of pre-recorded?
Yeah, so the question is like in the planetarium here, I'm operating the software live and flying us through it, turning stuff on and talking about it. And is that what happens in the planetarium? And it's a great question. Actually, we do a combination of 2 different things. We show pre-recorded movies, and then we also do live presentations. Like tonight, there'll be a live presentation about brown dwarfs. And what I like to describe it as like Transformers the movie and Transformers the video game. So I'm Transformers the video game. So like, if you know about this, like Transformers the movie has better graphics, but Transformers the video game is fun because you get to control the robot. You get to go anywhere. You get to look at it from any angle. You get to make it do whatever you want. And so when we make our rendered movie, we actually use the same software that they use to make Transformers and Dune, this program called Houdini, which is like a Hollywood level VFX program. But we'll actually work with the same data that people working, the digital artists and people making the movie will work with the same data that I work with in our live interactive software, and we'll combine. And in this last one, we actually did some things where we could like take flight paths from this software and use it in the movie to make flight paths through the data. And here I'm rendering, like right now with all this data on the screen, I'm rendering it at 74 frames per second. So like every second I'm generating 74 frames of this image as I move around. But when we're rendering the movie with all the data and all the everything for the planetarium movie, it's like maybe 1 second might take 4 hours. So that's like here I'm doing 75 in 1 second. And then they're doing 60 in 4 hours. So it's like a huge difference in the amount of data that is being looked at and the fidelity of. So one of the different like things we have to choose when we're working with this data and trying to visualize it in real time is where do we trim it, where do we cut it, what ways do we like change it. So like in this case, we have the main asteroid belt. I didn't actually show you every asteroid that we have the data for in the main asteroid belt. If I do that, it would like have a lot more of them. So here I just told it to show 10 times more asteroids in the main asteroid belt than it was before. And it's gonna like take a second to like recalculate it and recompute it. And it'll be like thicker and it will cost me a lot more to render, but it won't, like there it is. And now I'm down to, instead of 74 frames per second, I'm at 28 frames per second. But it like didn't really add that much to your like understanding of what's happening and to my story about the chaoticness versus the flatness, right? Like all it did was just get a little bit thicker. And so in this case, like one of the decisions we made was like show less of it for better performance. But all of the data is there when you download it and stuff too, which is cool because the users can decide and like which things they want to like put up or down and stuff like that.
I texted my wife because we just listened to a professor talk about dark matter.
Yeah.
Right? And, a little bit of, happy luck and circumstance. But this professor, and I'll find his name, I just messaged her, talked about how dark matter is actually creating kind of like a sphere around this entire system.
Yeah.
And we just, our methodologies and our tools are limited because dark matter, only the fringes of dark matter actually conduct electricity, right? So based on this visualization, it looks like there's a lot of other dark matter that surrounds this entire system and creates this shape. It's more spherical rather than like a pancake, so to speak.
Yeah, so great observation there based on what we showed and what you've heard. I guess the thing is, the one thing I'll say is that it's called dark matter because we can't see it. And so everything that we do know about dark matter is coming from we infer from our observations and from the data, and also from our simulations and models. And so in this case, I was just trying to load up a simulation that I had. And I had a couple different resolutions, so I was trying to load the better resolution one of the Milky Way and a collision with the Andromeda galaxy. Oh, okay, it's still loading up the higher resolution one, but maybe I'll go to Andromeda for a second. There's our simulation data of the Milky Way there. And here the green is stars in the disk and yellow is points of the what they call the halo stars, the stars that are like those more chaotic outside of the disk. And then as we zoom out, what we're going to see, if I make it a little bigger, is now in purple is the points of the dark matter simulation. And so can you see those purple points? And actually now over here, you're seeing Andromeda also over to the side. And let me make its points a little bigger. And like one of the really amazing, awesome things about this visualization for me when I worked on it with the scientists who came was like, here it's simulation data, but about the dark matter. And here I'm looking at the dark matter points. I've got the 2 different data sets on of Andromeda and of the Milky Way. And you may have heard about that they're going to like collide or whatever in 2 billion years. But what was so interesting to me was like, okay, I'm looking at the galaxies and these are the data. And then we have the dark matter points here. And like, to me, I was like, wow, they say we're going to collide in 2 billion years. But when I look at the dark matter, like the dark matter from the data sets has already collided. So like, in a way, like I'm seeing this, like these 2 different galaxies, which are super far away, as like one system now. Whereas before, they were 2 concrete things that in 2 billion years might collide. Whereas now when I'm looking at this data, I'm just getting goosebumps because I was like remembering the feeling of like seeing it and thinking about it was like these 2 million light year away galaxy is actually like part of our system. Like they're both, because that dark matter is connecting them. Let me turn off these other galaxies that are now like gumming up the works. But you see like they're, if you zoom out far enough, that's one system, like the stuff we've been seeing, right? And now we zoom in and there's the 2 individual concrete systems.
This is all open source too, so you can download it.
Yeah, it's all free. You could do OpenSpaceProject.com. You can just download this on if you have a PC, laptop, just download it at home and play around. And almost everything that I showed today comes with it. There was a couple data sets that I have like added myself and stuff. But almost everything I showed is just in there.
Micah, you talked a few times about like looking at the data with scientists. So I know that like primarily this is for public engagement, right? How often is it used for data visualization for in the service of science? Like,
yeah, great question. So yeah, I mean, we built it for the planetarium to give shows like I did today to talk to the public and stuff like that. But then we work with the scientists to bring their stuff in and stuff. And so as a result of all the years and the collaborations and the different academic things, we've had a number of times where we are actually just doing shows with scientists only in the planetarium for them to explore the data, look at it combined with different things. And those are some of the really fun, cool things. And I always love this funny story of one time when it was the Mars rover, Mars 2020 rover, before it landed, they had to pick the landing site out of these 3 sites. And they had a geology symposium up in the geology department in the museum. And afterwards we were giving them a show in the planetarium about our Martian visualization of the sites. And so one of the scientists said, "Oh man, this is amazing. I've never seen it like this." And I said, "Well, like, what do you mean? I downloaded this from your website. Like, what do you mean you've never seen it like this?" And he said, "Yeah, but we're always looking at it in 2D, like top down, so that they could just like extract the data from it. And they hadn't looked at it in this kind of like 3D, more like immersive type visualization, especially because we had them in the planetarium, which is like a 67-foot immersive screen. And so like this is the Jezero crater, ultimately the landing site that they picked. And so it was cool to hear them say that, like, here we were showing them their data in a different way that they hadn't seen before.
is this live imagery or is it simulation?
Neither. The question was, is it live imagery or a simulation? So this is real imagery, but I guess not live. Like
right,
this is,
live.
yeah, so this was a picture taken from the Mars Reconnaissance Orbiter, and in particular, its high-rise camera, which is like a zoom lens camera. So they have like the wide angle, the medium, and the zoom lens. And so this is the zoom lens has 25 centimeter per pixel resolution. So that means like if my laptop was there, it would show up in these pictures. And so that's like pretty amazing data. And then like like, you know, if like people were there, we would see them. And then one of the cool other things, that really important piece of data that we have here is the digital elevation model. And so they, in this case, they're able to use the two, like they take stereo pictures, 2 pictures from the satellite at different times, and they use the like ephemeris data of the satellite of like where it is, so they know like where it is when, and the focal length of the camera and the orientation of the camera. And so they could look at the difference in the lines in the 2 pictures and determine, oh, if it was here, and they make like triangles and stuff like that. And so they're able to like create a digital elevation model of the area. And so like from the pictures, they're able to like derive more data. So here, basically, now I just turned off the global elevation model, which embedded us in a thing, but maybe I'll turn that back on, and I'll just say, like, here's the high resolution elevation model that I'm gonna embed us in. And like, you'll see if I turn it off, look at how flat this area becomes. And so a huge part of the visualization here is visualizing this height map or digital elevation model, which is this, like, in this case, derived data from the stereo imagery. Whereas like if I turn that off and we look in the background, so in the background, it's a combined data from stereo imagery and a laser altimeter, like we were talking about on the moon. And then I could even have like a lower level data here is now just the laser altimeter data, but maybe that's actually, yeah, there it is, like only the laser altimeter data. And then I'll add the, you know, the medium level stereo data, which makes it like a little bit better. Right here, we can see like slight differences in the background mountains. But then when I add the high resolution stereo data, now we're seeing like really massive differences in the visualization. And so that was like part of what they had meant when they had said we'd never seen it like this. I think we'll end it there.
That was
on
great.
Mars.
Thanks, Micah.
Awesome. Thank you all.